Okay, now the fifth problem that we are going to look into is that of a combined gas and steam power plant. So there are going to be um, two different systems working together to produce work, and one of them is going to have gas as the working medium and steam, and the other one is going to be steam, uh, using steam as the working medium. These are the conditions given to us, but I would like to take you uh, through the question by using this diagram. So you have a combustion chamber, you have a compressor, you have a gas turbine. So this is the part where gas works, and this is the part where steam works. So it's compressed from fifth state to sixth state, the gas, and then it's uh, combusted, and then it goes into the turbine and gives out work. So there's work coming, WGT is what we are naming it. And that um, um, exhaust, the exhaust gases are used to heat up the steam in this cycle, which helps run the steam turbine. And these are the state. So we have fifth, sixth, seventh, eighth, ninth, first, second, third, and fourth. These are the states we where we are gonna try to, again, like in the previous problems, find the enthalpy on these states. For gas, the enthalpy formula that we are going to use is always going to be the change in enthalpy. Like if I want at just 7 minus at 6, so I'm going to use the mass into the specific heat at constant pressure into the change in temperature. So T7 minus T6. So always there's going to be this formula that I use uh, for gases, and for steam, this part I'm always going to use the steam table for calculation of enthalpies. So these are the conditions given to us. The pressure ratio was given to be 16, and that is why we have this thing out here: P6 by P5 equals 16. The temperature was given out to be 300 Kelvin. The temperature at which the air enters the compressor, it's 300 Kelvin. The mass flow rate of the gas of the air is given to be 14 kilogram per second. The temperature at exit of the combustion chamber, 1500 Kelvin. Temperature at the inlet of the steam turbine was given to be 400 degrees centigrade. The pressure P3 at which the steam turbine operates is 10 megapascal. T4, and the exhaust temperature of the steam from the turbine, it's 420 Kelvin, and P4 is 15 kilopascals. We have to find the mass flow rate of the steam and the net amount of work done and the efficiency of the cycle. So again, the compressor work, uh, I've already explained that the compressor work and other quantities you are going to ignore uh, the kinetic energy changes and the potential energy changes. And since uh, the amount of heat transfer is so this is the formula for the amount of work done, where WCP equals to m dot A into H5 minus H6. How has it come out to be like that? Because of the change in enthalpies are going to give you the amount of work done. Okay, so we are actually using steady flow energy equation, and uh, after ignoring all the quantities which are not relevant, we come to the point of amount of work done being equal to this much. Also, this is the isentropic relationship. Isentropic relationship T6 by T5, and where gamma is the adiabatic constant for air, which is 1.4. So using all of that, I get the temperature T6. So that helps me calculate the amount of work done in the compressor, which comes out to be negative. The negative is obvious because the compressor is working on the air, on the gas, so if the amount of work done is going to be negative, it's going to require work. That's not a point, but still this amount of work is something that we should focus on in our calculation. So it's going to play a part in the amount of net work done in the whole binary cycle of ours and the whole combined cycle of ours. Combustor again takes the state of the gas from the sixth state to seventh state. That is why the amount of heat transfer comes out to be this much. And using the temperature, um, a constant specific heat at constant specific heat, and all of these quantities, you get the amount of heat that you have given uh, in to the combustor for taking the gas from state 6 to state 7. So that comes out to be 11780 kilowatt. A gas turbine is obviously the working system in that part of our cycle. So the amount of work done in that um, turbine is going to be at 7 minus h8, and the mass of air flowing through it, which comes out to be uh, m dot a cp into t7 minus thc. My uh, See, once we have understood that uh, the gas flows from this state to another state in um, in a cycle, and all we need to do is to find the enthalpies at various states. That's more than half of the part done. So in this chapter we are only going to focus on calculating the enthalpies and understanding how the cycle, how the working medium, which is steam or gas in our system, how is it moving from one state to another. That is what we are going to focus on. Rest everything is thermodynamics, which we have been studying. So the temperature pressure relationships, and the steady flow energy equation for an open system. So these are all open systems, so using steady flow energy equation and things like that. So that's why it all becomes very easy from there. So amount of work obtained from the gas turbine comes out to be 11550 kilowatt, again using the temperature pressure relationship to get the temperature T8, using that T8 to calculate the amount of work done by the gas turbine. Again, heat exchanger, I'm using heat balance here, but only trying to calculate the amount of heat that has been extracted from the uh, exhaust gases from the gas turbine. I'm going to calculate the amount of heat extracted from these gases. So that comes out to be 3648. And since it's being extracted, there is a negative sign here. 3648 kilowatt is what we are going to provide to the steam for its conversion from liquid to uh, vapor. So calculations for enthalpy of steam at state 1, 2, and 3 and 4. So again, it's going to be right from our steam tables. So the first state is its entry into the pump, so which is that of a saturated liquid. So obviously finding out the HF at 15 kilopascals, which comes out to be this. Now this is the formula that I use for the pumps, always H2 equals to H1 BF1. So that gives me H2 equals to 236.1. State 3 is a superheated state, and that's why this is when the superheated steam enters the turbine. So H3 is going to be the enthalpy at 10 megapascals and 400 degrees centigrade, which comes out to be 3097.5, which can be observed from the superheated steam table. And entropy comes out to be 6.2141. State 4 is wet steam, because the third state and fourth state entropies are same because of the process being isentropic. And again, the uh, entropy of gas at 15 kilopascals is larger than the entropy S4. That is why we assume that this is a wet state, and S4 can be calculated, uh, and X can be calculated using this formula. So X comes out to be 0.7528. Again, using that value of X, we're going to get the value of H4, which comes out to be 2012 kilojoule per kg. See, again, I'm following um, my old pattern of calculating enthalpies at various states, and again applying the heat balance in the heat exchanger. So this was the amount of heat we extracted from air, and this was the amount that the steam is going to receive. So this is the steam end, and this is the uh, air end. So burnt air and end. So the amount of mass flow rate of steam can be calculated using this expression right here. So it comes out to be 1.275 kilogram per second. However, we have already calculated this above. It's not that necessary. We could have written simply the amount value that we calculated earlier. But again, just for the sake of explanation, the mass flow rate which was asked comes out to be 1.275. Now it becomes very easy to calculate the amount of work done by the steam turbine, third state, fourth state enthalpies, and the mass flow rate of the steam. So the mass flow rate of the so the amount of work done by the steam turbines come out to be 1384 kilowatts. Amount of heat lost uh, when the steam passes through the condenser and converts into saturated liquid. This can be calculated by mass flow rate of steam into H4 minus H1, which comes out to be 2277 kilowatt. Amount of work done work required by the pump can be calculated using this expression, because the pump is responsible for taking the saturated liquid from state 1 to state 2. That is why applying the um, SFEE, the steady flow energy equation between state 1 and state 2, gets us the amount of work required by the pump, which comes out to be 12.95 kilowatt. So the net amount of work done by the dual cycle, or what should I say, this combined cycle, comes out to be the work done by the gas turbine, work done by the steam turbine, minus work required by the compressor, and the work required by the pump, which comes out to be 7821 kilowatt. Now that gets us to the value of thermal efficiency, which comes out to be amount of uh, net work done divided by amount of heat supplied, which we have already calculated above, and that gives us the value of efficiency, which is 66.37, very very high as compared to that uh, um, as compared to the values that we have calculated earlier in case of Rankine cycles or regenerative cycles, which was usually around 44%. I think in the last lecture we saw that it was around 42%. So this is a very this is highly efficient cycle right here, 66%. So this was it. This was the fifth problem, and I'll see you in the next lecture. You have a good day. Bye bye.